Before we start extracting segments from the dataset, we must ensure that the data is in good shape. We call this step of the market segmentation analysis process exploring data. Data exploration has two aims. First, we want to gain insight into the dataset and the variables it contains. Having a good understanding of the data helps us select a good method of analysis, and it also prevents us from misinterpreting results. Second, we need to get the data ready for segment extraction. This means checking for errors which may cause potential problems in the later stages of market segmentation analysis. We need to clean the data, and if there are any errors, we need to fix them immediately. In addition, further pre-processing steps might also be necessary. Many errors and inconsistencies can be present in the data. Missing values, values outside of the permissible range, incorrectly or inconsistently labeled variables. Before extracting segments, we need to clean the data. If values are missing, we need to decide whether to remove the respondent or remove the variable, or whether to impute values based on a method that allows making a best guess of what the value should be. We need to check if values entered for the variable are within the permissible range. Variables also need to be labeled correctly and consistently. Going through these steps makes extracting segments easier later on. Once we know that the data is free of errors and complete, we need to explore it. Why is this so important? Because when we conduct complex data analysis, we lose touch with the original data. We only interpret the results. Without understanding the basic characteristics of the data, we risk misinterpreting results. We can explore data using descriptive numerical analysis or graphical representations. Descriptive numerical analysis provides insight into two important properties of the data: how values of each variable are distributed and how they are associated with one another. To learn about the distribution of nominal, binary, or ordinal variables, we can use frequency counts. These variables are also called categorical variables. To learn about the distribution of metric variables, we can use summary statistics. To learn about associations between variables, we can use cross-tabulations for two nominal, binary, or ordinal variables. For a nominal, binary, or ordinal and a metric variable, we can group the data corresponding to the values of the categorical variable and calculate group-specific summary statistics for the metric variable. For two metric variables, we can use correlations. The second approach for gaining insight into the data is to plot them, to create graphical representations. We all know that pictures say 1,000 words. They also say 1,000 numbers. This is why statisticians are heavy users of graphic representations when they try to understand a dataset. Commonly used graphical representations are bar plots, scatter plots, mosaic plots, box plots, and histograms. We will discuss the histogram and the box plot in a bit more detail. Histograms can only be used with metric data. They plot the values a variable can take along the x-axis. They plot how frequently each of those variables occurs along the y-axis. Histograms are useful for checking if the distribution of a variable is unimodal and symmetric or skewed. To draw a histogram, we first need to create intervals of values of the variable of interest. We use those intervals to determine how many data points fall into each one of those intervals. These frequencies are then plotted onto the intervals, displaying the distribution of the variable. In the histogram you see here, age is the variable of interest. We split up the metric age variable into intervals of approximately 10 years and plot the frequency of people within each one of those age intervals along the y-axis. If the variable is binary, nominal, or ordinal, the equivalent graphical representation is the bar plot. If we are exploring a metric variable and we do not want to create intervals artificially, we can use a box and whisker plot or box plot. A box plot shows the minimum, first quartile, median, third quartile, and the maximum value of a variable. These 5 numbers are referred to as the 5-number summary. The box plot for age is shown in the middle of the figure you see here. We see that the youngest person is 18 years old, because the left vertical line is at 18. We can also see that the oldest person is 105 years old, because the right vertical line is at 105. 25% of respondents are between 18 and 32 years old. That's the distance between the left vertical line and the left vertical border of the box. 25% of respondents are between 32 and 42 years old. 42 is the median, and it's depicted by the thick vertical line in the middle of the box. 25% of respondents are between 42 and 57 years old, and the final 25% are between 57 and 105. The actual data is plotted below the box plot in this illustration. Many other ways of graphically visualizing data exist. We will discuss a few more when we talk about profiling and describing segments in steps 6 and 7. Data exploration may indicate that we need to do something to the data before we can extract segments. We call this pre-processing. 3 common kinds of pre-processing are categorization or recategorization, standardization, and reduction of dimensionality. Merging a certain range of values is one form of categorization. When we defined age groups earlier, we categorized the data. Standardization is necessary when our segmentation variables have different scales. For example, we may have a binary variable, buying or not buying a product, and a metric variable, age. The buying variable ranges from 0 to 1. The age variable ranges from 18 to 105. During segment extraction, age would have a much stronger impact than buying. To avoid this, we adjust the values such that they are on a comparable scale. That's standardization. Reduction of dimensionality is sometimes used when there are too many segmentation variables given the sample size. Principal components analysis finds uncorrelated new variables, components, which retain as much of the original variable information as possible. Still, much information is lost, typically 40 to 50% if only the first few principal components are retained. However, which part of the full information in the data is valuable for clustering is not known. So replacing original segmentation variables with a small set of principal components is not recommended in market segmentation analysis. Our demos in this module show how the procedures we've discussed in this video can be calculated.